Hello and welcome back. We now look at a few other statistical properties, in particular the correlation between variables. And here we want to investigate how easy it is to introduce spurious correlations. That means that they're correlations that are not real, but they're an artifact of the way, for example, that we record the data. We take a very simple example and imagine that we have two six-sided dice. We can use the function from NumPy random choice to simulate rolling that dice. So let's start off with two independent dice, and we take one of the sequence 1, 2, 3, 4, 5, 6 and draw a large number of random throws of this virtual dice. And then we can use the NumPy function and the correlation coefficient to determine the correlation between these. And of course, because they're independent dice and we roll them independently, we don't expect there to be a correlation apart from some numerical fluctuations, because we're dealing with random numbers and a finite set of those. So this is what we observe. Here is the correlation between those two numbers, and it's more or less zero. We can also draw a histogram of all the numbers that we have generated. And when we look at the histogram of the numbers, we see that they're fairly uniform. This is what we expect. We can also look at a 2D histogram of those two numbers, where we plot the numbers of dice 1 on the x-axis and dice 2 on the y-axis, and we would expect a fairly uniform distribution. So for each number of one dice, we get all the other numbers because they're independent. So this is uncorrelated random variables in the parlance of statistics. But now we modify this a little bit. We do a little intervention. We only record the numbers with one of the dice shows either a 5 or a 6. Of course, this is a stupid thing to do, but it illustrates the point that the way we record the data has great impact on what we observe. So here we do the following. We have an empty list, then we throw the number, but only one random number now at a time, and then we check if we have a 5 or a 6 for those two dice, and if yes, then we append the random number we've just generated. Now we would expect a strong correlation, and this is what we see. They're fairly strongly negatively correlated, and this is because we can only record the number if there's a 5 or 6 present. So although the dice themselves are, of course, uncorrelated, the way we record our data has a strong impact. When we look at a histogram, we can also see that now, of course, the numbers 5 and 6 are much more prevalent compared to all the other numbers. And if you look at the 2D histogram, we see this funny box shape, which is essentially the same thing as this here. We can think of it about this like we change the way we record the data, and then we observe a change in the outcome. So this is fairly obvious, and we understand why this is happening and how we did it. However, in most realistic situations, we start from a very different premise. We obtain the data somehow in our experiments, or maybe we are even given the data from somewhere else, and we may not know how the data were acquired, or even if we know how the data are acquired, we need to think very carefully if the process of generating this data, of measuring the data, can introduce such a spurious correlation. Like, for example, if we just have this data and start with a naive task of building a predictive model of dice, then we would assume that this strong correlation that we have observed is real in this. And essentially, this is also the assumption that machine learning does. If we have a correlation in the data, we assume that this is a real correlation. And this highlights the importance of understanding not only where the data we use comes from, but also how it was measured.